Hello, calculus students. Miss Deer back on the mic with you today to go over some extra polar practice. So just to quickly sketch a graph, let's let R equals, let's pick 2 times 1 minus sine theta. So again, if we're going to sketch this, we're going to plug in our 4 absolute favorite theta values. So when theta is 0, sine is 0, so I start out at the point 2, 0. At pi halves, sine of theta is 1, so 2 times 1 is, or 1 minus 1 is 0. At pi, sine again is 0, so I'm out here at 2. And at 3 pi halves, I have negative 1. So 2 times 1 minus negative 1 is 4. So connecting the dots, moving in a positive theta direction, I come here, I come here, I get bigger and bigger and bigger and bigger and bigger. Oh, I missed my dot. Make my dot bigger. So here's my peach graph. So the period of this graph is 2 pi. It took me 2 pi to get all the way back over here. So here's 2, 0, 0 pi halves, 2 pi, and 4, 3 pi halves. So let's find dy dx when theta equals pi. So again, we can see that dy dx is going to be the slope of this line right here. So when theta equals pi, again, I'm at the point 2 pi. If I wanted to actually convert this to rectangular coordinates, this is the point in rectangular, this is the point negative 2, 0. So to find dy dx, I have to find dy d theta over dx d theta. Y is r sine theta. X is r cosine theta. So to find dy dx, I'm going to do dy d theta over dx d theta. So I'm going to get to use my product rule here. So I'm going to get sine 2 times sine theta times negative cosine theta plus 1 minus sine theta times cosine theta all over 2 times cosine theta times negative cosine theta plus 1 minus sine theta times sine theta. And again, I'm evaluating this at the point when theta is pi. So when theta is pi, sine is 0. So this term is going to disappear, and this term is going to disappear. These are going to cancel. So I get 1 minus 0 times 1 over 1 times 1, 1, 1. I got 1. So the slope of this line is 1. If I wanted to come up with the equation of the tangent line, I would get y equals 1 x plus 2 plus 0. Now at this same point, we can actually find dr d theta. And I want to be very clear that, again, if I want to find, so dy dx at theta equals pi is 1. This is the slope of the tangent line. If I want to find dr d theta at theta equals pi, this is asking what is happening to the distance from the origin out to the curve. And we can see that it's getting bigger, 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 bigger until 3 pi over 2, and it's getting smaller, 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 smaller. So if I wanted to find dr d theta at theta equals pi, then, well, r as a function of theta, r is 2 times 1 minus sine theta. So dr d theta is going to be 2. The derivative of 1 minus sine theta is negative cosine theta. And I can evaluate this at theta equals pi. So at theta equals pi, dr d theta, when theta, is it still on the screen? Theta equals pi, I get 2 times negative 1, which is 2. So the rate at which my r values are increasing is 2. The slope of my tangent line is 1. So again, working with this same graph here, we can find the area of my squishy peach. So my area, well, again, it matters very much that my period here is 2 pi. So my area is going to be the integral from 0 to 2 pi of 1/2 r squared d theta. R is 2 times 1 minus sine theta squared d theta. And I could find the arc length. Again, to travel the entire curve takes 2 pi. So my arc length is the integral from 0 to 2 pi of the square root of f of theta, which is r. So 2 times 1 minus sine theta squared plus f prime of theta squared. Let's make this go all the way out here. The derivative of 2 times 1 minus sine theta is 2. The derivative of 1 minus sine theta is negative cosine theta squared. I don't think there's anything else we can do to this one. We could figure out when the derivatives are 0, which would be here and here. Also down here. I could figure out when my derivatives would be undefined, which would be right here. That's about all the fun that we can have with this one.